Hi there, and welcome to this lesson on Pure Mathematics 2. In this lesson, we're on Chapter 1, 1.6, and we'll be looking at two different types of proof. Proof by exhaustion and proof by counterexample. Proof by exhaustion breaks down what you're trying to prove into separate cases or categories, and then proves each case individually. Proof by counterexample is a method for proving that a statement is false. Example 1. Prove that for any integer x, the value of f of x equals x cubed plus x plus 3 is an odd integer. Now, the easiest way to prove this is by using proof by exhaustion and looking at the odd and the even integers separately. The way we do that involves a very important method, and a method which is used frequently on this type of question. First of all, the even integers. All even integers n can be written in the form n equals 2k, because they're all multiples of 2. All odd integers m can be written in the form m equals 2k plus 1, one more than an even number, where in both cases k is itself an integer. So what we're going to do on this question is first of all assume that x is even, so we'll let x equal 2k and substitute that into the expression, and then we're going to assume that x is odd. So we'll let x equal 2k plus 1 and substitute that in. And in both cases, we're going to try and prove that the result is an odd integer. I'll let you have a go at doing that yourself. So pause the video, have a go, and then come back to me when you're ready. Okay, let's have a look. So first of all, we're going to let x be even. Now, if x is an even integer, it can be written in the form x equals 2k. And that's what we substitute into x cubed plus x plus 3. So we'll get 2k cubed plus 2k plus 3. Cubing that bracket gives us 8k cubed plus 2k plus 3. And it's this next step which is not intuitively obvious. We essentially factorize by dividing all these terms by 2. And that gives us 2 into 4k cubed plus k plus 1. Now, 2 times 1 is 2, so we get a remainder of plus 1, which goes outside the brackets. This expression inside the brackets must be an integer, so we've got 2 times m plus 1, where m is an integer. And what that means is that if x is an even integer, we've shown that the value of x cubed plus x plus 3 must always be an odd integer. Now we do the same thing again, but this time assuming that x is odd. Well, if x is odd, it can be written in the form x equals 2k plus 1. And we substitute that into the expression, which gives us 2k plus 1 cubed plus 2k plus 1 plus 3. And if I cube this bracket, I will get 8k cubed plus 12k squared plus 6k plus 1 plus the other two terms. And then tidying all of those up gives me 8k cubed plus 12k squared plus 8k plus 5. Now we do exactly the same as we did in the case where x was even. We're going to factorize by dividing by 2, which gives us 2 into 4k cubed plus 6k squared plus 4k plus 2. And 2 times 2 is 4. So again, we get a remainder of 1, which we write outside the bracket. This term in the brackets must be an integer. So we have something of the form 2m plus 1, where m is an integer. And what that means is that if x is an odd integer, then the value of x cubed plus x plus 3 will also be an odd integer. Now we just need to finish the question off. And the way we do that is just really by writing a statement which shows that we've done everything we were asked to do. So finally, we'd need to write something like, since all integers are either odd or even, we have shown that for any integer x, the value of f of x equals x cubed plus x plus 3 is always an odd integer. Okay, example 2. It turns out to have a very similar method to the first example we've looked at. This time we were asked to prove by exhaustion that the product of any 3 consecutive integers is always an even integer. What does that mean? Well, 3 consecutive integers are like 3, 4, 5, or 10, 11, 12. Product means we're going to have to multiply those 3 numbers together, and then we're going to have to prove that the answer is always even. Once again, we're going to use this idea that we can consider the even and the odd separately. The first time round, we'll assume that the first number is an even number. So the first number can be written in the form 2k. The second number will be one more than that, the third number, one more again. Then we'll have to multiply them together and show that what we've got is even. Then we'll have to repeat the process, this time assuming that the first number is odd. I'll let you have a go at doing all of that. So pause the video and come back to me when you're ready. Okay, let's have a look. So first of all, we assume that the first integer in the sequence is even. If that's the case, then the three integers can be written in the form 2k for the first one, so that it's even. The second one has to be one more than that because they're consecutive, and the third one has to be one more again. Then we're going to have to multiply those together. Now, if I multiply these three terms together, I do get 8k cubed plus 12k squared plus 4k. And then we do exactly the same as in the first example. We're going to divide all of this by 2, taking 2 outside the brackets, which gives us 2 into 4k cubed plus 6k squared plus 2k. But this time there is no remainder. Now this term inside the brackets must be an integer. So we've got 2 times m, where m is an integer, but no remainder. What that means is, if the first integer is even, the product of the resulting 3 consecutive integers will itself be an even integer. Now we need to do the same thing again, this time assuming that the first integer is odd. If the first integer is odd, then we'll write it in the form 2k plus 1. The next integer up from that, add on 1. Next integer up from that, add another 1, because they're consecutive. Then multiply them together. Now if I multiply these 3 brackets together and collect up all the terms, this is what I get. 8k cubed plus 24k squared plus 22k plus 6. Then we divide by 2, factorizing, which gives us 2 into this. And again, 2 3s are exactly 6. So there is no remainder, which means we have something of the form 2 times m, where m must be an integer. What that means is that if the first integer is odd, the product of the resulting 3 consecutive integers will be an even number, 2 times m. Finishing the thing off, therefore, since the first integer can only be even or odd, we have shown that the product of any 3 consecutive integers is always an even integer. Okay, example 3 should be familiar from the last lesson, which we proved using an algebraic method. This time there's a lot quicker method to use. So example 3 has the statement that 2 is the only number, which gives the same answer if you square it or if you double it. So for example, if you square 2, you get 4. If you double 2, you get 4. But this time we're asked to prove by counter-example that the statement above is false. That means we just need to find any other number other than 2 where that works. Now, if you remember the last lesson, you'll remember a number that does work as a counter-example. And that number is 0. Because if we square 0, we get 0 for the answer. If we double 0, we get the same thing. We get 0 for the answer. And then all you'd have to write down is, therefore, since we have found a counterexample, we've shown that the statement is false. Okay, the last example in this lesson is quite a lot more tricky. We're asked, first of all, to prove by deduction, that was the method that we learned in the last lesson, that x over y plus y over x is greater than or equal to 2, as long as x and y are positive. The second part is actually a lot easier. Proof by counterexample that the statement is false if x and y are not both positive. Now, with questions like this, it can be very difficult to know how to start. This statement is not obvious. You wouldn't just look at it and say immediately that it's clear that x over y plus y over x is greater than or equal to 2. One approach to this type of question, which can be fruitful, is just to keep on rewriting this question, this expression, until we get a form which does look obvious, which would make it a lot easier to prove. Now, I'll let you have a go at seeing if you can do that yourself. It is quite tricky. But have a go and then come back to me when you're ready. Okay, let's have a look. Now, what I'm going to do first of all is just move all of the three terms over to the left-hand side. So taking away 2 from both sides would give me that. This is an inequality, it's not an equation. Now, you can basically use the same methods to solve inequalities as for solving equations, but there is an exception. With inequalities, what you cannot do is either multiply or divide by a negative number or by a number which may be negative. So that matters later on in this. But first of all, we've got 3 fractions here. That last fraction would be minus 2 over 1. We're going to add them all together to get 1 fraction, which means we need a common denominator of xy on the bottom of the fraction. Adding those together will give us this. If ever you add fractions together, it's a good idea just to quickly check that it looks right. Now, if I have x squared over xy, 1x will cancel from the top and the bottom, leaving me with x over y, which is what I want. The middle term, y squared over xy, 1y cancels from the top and the bottom, leaving me with y over x, which is what I want. And then this last term, minus 2xy over xy, both the x and the y will cancel, leaving me with just minus 2, which is what I want. So all is well. What we do now is we're going to move the xy to the other side. What's really happening is we're multiplying both sides of this inequality by xy. Now that'll give us x squared plus y squared minus 2xy on the left-hand side, and xy times by 0 is 0 on the right-hand side. It is important with this that you write down that we're allowed to do that because we can only multiply both sides of an inequality if xy is positive. But we know that it is because of what they told us in the question. So they've told us that we're only trying to prove this for positive values of x and y. Well, if x and y are both positive, that means xy itself is also positive. So there's no problem doing that. And then this last step is factorizing that. X squared plus y squared minus 2xy can be factorized to give x minus y squared. And it's only when we get to this point that you have a statement that does look obvious. That's saying we've got to prove that if you square something, it'll either be greater than 0 or equal to 0. Well, we know that's the case. If you square something, you never get a negative number for the answer. It'll either be a positive number greater than 0 or it could equal 0, but it's never going to be negative. So whilst this statement at the beginning was not obvious, what we've done is do algebraic work on it until we've managed to get to a statement that is obvious. And now what we do is we use this statement as the starting point for our proof. And we reverse the whole argument, going back one step at a time till we get back to the beginning, which is what we actually want to prove. How does that happen? So we consider x minus y squared. And as we just said, well, x minus y squared has to be greater than 0 for all values of x and y, because all squared numbers are greater than or equal to 0. Then we'll square the brackets. That gives us x squared plus y squared minus 2xy has to be greater than or equal to 0. Then we're going to divide by the xy, and we can divide by xy because we know that xy must be positive because both x and y are, which is what that says there. And then we're going to divide each term individually by the xy. So x squared over xy simplifies to x over y squared over xy simplifies to y over x, and minus 2xy over xy simplifies to minus 2. So we split it up into the 3 separate fractions. And lastly, all we have to do is add 2 to both sides of the inequality, and that'll give us x over y plus y over x has to be greater than or equal to 2, which is what we were asked to prove. So we just need to write down that we have done that. Therefore, x over y plus y over x is greater than or equal to 2 for all positive values of x and y. Now, part 2. Part 2 asked us to prove by counterexample that this statement is false if x and y are not both positive numbers. Now that just means we've got to find a pair of values for x and y where at least one of them is negative and the answer is not bigger than or equal to 2. Many pairs of values would work. The one I've chosen to use is x equals 2 and y equals minus 1. So that's the negative number. If x is 2 and y is minus 1, then x over y plus y over x is equal to 2 over minus 1 plus minus 1 over 2, which is minus 2, take away a half, which is minus 5 over 2. Now, minus 5 over 2 is less than 2. It's not greater than or equal to 2. Therefore, since we found a counterexample, we have shown that the statement is false if x and y are not both positive numbers. Okay, that gets us to the end of this lesson. If you've got the textbook, turn to page 19 and have a go at exercise 1F. Thank you very much for listening and cheerio.